We're looking today at graphing rational functions. This is definitely a challenging lesson, so have your notes handy, slow down as you need to, and take your time with the video. So, here we go. First of all, a rational function is one which has a variable in the denominator. So, one to start with is f of x equals 1 over x. So we're going to graph that as sort of like a y equals 1 over x function. Now the first thing to notice is that x is in the denominator. And so we could plot values, but we know that if we plug in 0 for x, we will get, you can't have 0 in the denominator, so you'll get an infinite answer. So that point is not going to work. If we plug in 1 for x, we'll get y is equal to 1. We can plot in some other points. If we plug in 3, we're going to get y is 1/3. If we plug in 1/3, we'll get y is 1/3. So I can plot a couple of points, and they start to make this kind of interesting curve. If I start plotting negative values, I plug negative 1/3 in for x, so I get 1 over negative 1/3. That's going to be negative 3, and so forth. If I plug in negative 3 in for x, I get negative 1/3. So when I plot all those points on my graph, I get these interesting new type of a look. If I want to connect the dots, they're going to look like this. So here's the same function. A whole bunch of points are already provided. We graph each of those points. Again, this is the same graph we just saw a second ago, except with more data points. What we find is that the curves, they approach, but they never actually touch the x and y axis. So in other words, as x goes to infinity over here in this area, as x goes to infinity, then the y value gets closer and closer to the x-axis but never actually touches it. As y goes to negative infinity, again that curve gets closer and closer but never actually touches it. And these two lines, the x and y axis in this case, we call those asymptotes. An asymptote is a line where your curve is going to approach but never touch or cross. Okay, we have this rational function x over x squared minus 4. We can simplify it and rewrite it as x over x plus 2 times x minus 2. And we realize that we're going to have some problems when x is equal to negative 2 and x is equal to 2, because in those places our function is undefined. And so when our denominator is equal to 0, that can't be true, so we have an issue. So what happens when we look at the graph? So I just graphed this with a little graphing calculator so you could see what happens. Let's look what happens when x equals 2 and x equals negative 2. You can see that the graph functions never actually touch those values for that domain. So when x equals 2, when x equals 2 and when x equals negative 2, at those values for x, there is no y value. We say that those are vertical asymptotes, vertical as in up and down. But then the curves themselves of the graph never actually touch. They approach, they come very, 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 very close, but they never touch and they never cross. Notice that the graph of the actual curve is interesting. And these are, tricky to graph when you have to plot in points and see what happens. So you have one curve here, you have another curve here, and you have another curve here. As you practice, you'll get good at finding where these graphs go once you know what the asymptotes are. Okay, let's keep going. So, graphs of rational functions can have vertical and horizontal asymptotes. They're the lines the graph approach but not cross. Now, to find the vertical asymptotes, we look for the zeros of the denominator. In this case, 1 over x minus 4, a zero denominator means just take x minus 4, set it equal to 0, find the value where it's undefined, x is equal to 4, and that is where you're going to have your asymptote. Okay, so there's your vertical asymptote in this particular case. Okay, so vertical asymptotes come from the zeros of your denominator. Alright, so in this case, I want to find the zeros of the denominator, x squared minus 1. We can set x squared equal to 1 and find x is plus or minus 1, or we can factor it and get the same thing. In this case, we're going to get x is equal to 1 or negative 1. So there's my two vertical asymptotes for this given function. Again, we take the denominator and we find the zeros of the denominator. That will give us our vertical asymptotes. I'm not going to worry about the rest of the graph now. We're just focusing on asymptotes. Okay, so this is what the graph actually looks like, and you can see that the asymptotes drop in there at x equals 1 and x equals -1. Again, interesting looking curve above and below the axis. Okay, so now again, we're just focusing on vertical asymptotes. All right. So let's talk about horizontal asymptotes. Horizontal asymptotes of a rational function are determined by the following rule. If the denominator is of a higher degree than the numerator, then the horizontal asymptote is the x-axis. Okay, so if the denominator is a higher degree, notice that we have an x squared function here, and then we just have an x to the first function up there. So the denominator has a higher degree than the numerator. So in this case, the horizontal asymptote will be on the x-axis. And you might ask yourself, why is that true? If you think about what's happening as x gets closer to infinity, as x becomes the number infinity, then what happens to your function? And you realize that as x goes to infinity, g of x is getting closer and closer to 0. Let's look at the function. So if I plugged in infinity for x, I'd get 4 times infinity over infinity times infinity minus 1. That infinity times infinity is a really, really big number. That's going to grow really, really fast and get really large. So it turns out what you generally have is 1 over infinity. And 1 over infinity is essentially a really, really teeny tiny number, or almost an approaching 0. And so that's what's going on. If you have a higher degree in your denominator than you have in your numerator, then that function is going to approach 0 at as x gets higher and higher. So you're going to have a horizontal asymptote there. Okay, if the denominator and numerator are of the same degree, okay, so you have an x above and you have an x below, or let's say you had x squared above and an x squared below, if they have the same degree, then you look at the ratio of the leading coefficients of the numerator and denominator. Okay, so the leading coefficients in this case, you're going to have 2 in the numerator and you're going to have 1 in the denominator. So you're going to get 2 over 1, which is 2. And that's where your horizontal asymptote is going to go. You just find the ratio of those leading coefficients. And so in this case, it's going to be at y equals 2. And so our graph, we go up 2, and there's our asymptote right here. And that's what our function looks like. Okay. If you want to think about why that is, if you think about 2 times infinity over infinity plus 2, so infinity plus 2 is essentially the same as infinity. So basically your infinities are going to cancel and you're going to approach 2. Just to give you an idea of why that might be true. You can just memorize the rule, but it's helpful to know why it works. Okay. Zeros of the numerator are the x-intercepts of the graph. Plugging in a 0 for x gives the y-intercepts. So we want to know the intercepts. That's helpful when you're plotting these graphs, is to plot the intercepts. So an x-intercept is when y is equal to 0. And so in this case, it doesn't really work out. You go 0 equals 1 over x. You multiply both sides by x, you get 0 equals 1. So there is no x-intercept. And then for the y-intercept, you plug in 0 for x, you're going to get y is 1 over 0, and that's infinite, so that doesn't have an intercept. And that makes sense, because if you think of what that graph looks like, we looked at it a minute ago, it has this funny curve with asymptotes on the axes, and so it never does cross the x or y axis. There are no intercepts, so that makes sense. Let's look at the next one, x minus 1 over x squared minus 4. We want to know where the x-intercept is. Well, then just plug in, figure out what y equals 0, or g of x equals 0. When you multiply, you're going to get 0 equals x minus 1. Again, what we said is that if you want to find, okay, let me multiply this out, x minus 1 equals 0, so x equals 1. If you want to find the x-intercept, look for the 0 of the numerator. So the numerator up here, I'm a different color, the numerator up here, the 0 of that numerator, x equals 1, so that's going to give you that intercept. And then the y-intercept, plug in 0 for x, and we're going to get y equals 0 minus 1 over 0 minus 4, which is 1/4. So in that case, your intercept is going to be 1/4. Another way to do it is just plot like we had before, make a little t-chart, plug in 0 for x and 0 for y, and see what you get. plug them back into the function. In this case, if I plug 0 in for x, I'm going to get 1/4 for y. If I plug 0 in for y, or g of x, then I'm going to solve and get 1 for x. And by the same token, on the other one, you make your little t-chart. You plug in 0 for x, and you get an infinite solution, or undefined. You plug in 0 for y, same thing, undefined. There's no intercepts. So that's another way to look at finding the intercepts. Okay, so this is what those graphs actually look like, and it makes sense that you got no intercepts for the f of x equals 1 over x, because it does not cross the axis anywhere. And then the other one, it does cross. The y-intercept is at x equals 0, 1/4, and the x-intercept is at y equals 0, x equals 1. So that's what those graphs look like. You can see where they actually cross the axes. Okay. So here's an example problem. We're going to work all the way through it. We have a function, we want to find the asymptotes, and then we want to graph it. So first, find the asymptotes, then find the x, y intercepts of the function, and then sketch it by plotting a couple of extra points. So we'll start with the asymptotes. The vertical asymptote, remember, you want to find the zeros of the denominator. So x minus 2 equals 0, or x equals 2. And so we're going to have a vertical asymptote right there. Okay? Now, horizontal asymptote, remember we look at the order of the denominator versus the numerator. In this case, you have a higher order x to the first value for the denominator, so we know that the horizontal asymptote is going to be on the x-axis. Because it's going there to pick up. Okay, so we get our x-axis. Now we're going to go ahead and plot our x-intercept and y-intercept. So we plug in 0 for x. I get 1 over 0 minus 2, which is 1 over, negative 1/2. So I can plot that point, and there it is. If I plug in 0 for y, I'm going to get 1 is equal to 0. That makes no sense. So there is no y-intercept. There is no x-intercept. There's no variable y equals 0. So that one I can't plot. Now, to plot the rest of the points on the graph, I want to just come up with a couple of points and see where I land. So let's go ahead and try x equals 3. When I plug in x equals 3 into the function, I get 3 minus 2 in the denominator. 3 minus 2 is 1, so I get 1 over 1, which is 1. So 3, comma 1, that's a point right there. If I try another point, like 1, then I plug 1 minus 2 in the denominator, and I get negative 1. So 1 over negative 1 is negative 1. So I can plot that point. And just like this, I'm just going to go find a couple more points and plot them and see what I get. And then once I get just a couple points, I kind of recognize the pattern. I know I've got my asymptotes. I know generally where the graph is going to go. So just with a few points, I can really sketch the curve. And it doesn't have to be exact. You just want to get a general sense of where the curve should go. Okay, so that gives you a look at what our graph is. And notice, if you do, that this 1 over x minus 2 is just your 1 over x function shifted to the right by 2. So there's the parent function shifted. Parent function of 1 over x is the very first graph we looked at. So we just shifted 2 to the right. Okay. There is the function graphed nice and neat with a graphing calculator. Okay. Determine the locations of the asymptotes and the x-intercepts of each function, then sketch each graph. Okay, so start with the asymptotes. Again, we want to find the vertical asymptote. We look at the denominator, and we try to figure out what the zeros are. So I say x plus 1 equals 0, so x is equal to negative 1, and I can plot that asymptote. Now, horizontal asymptote, I look at the order of the two, denominator and numerator. It looks like they're the same order, so I look at the leading coefficients. The leading coefficients are going to be 1 over 1. So my horizontal asymptote is just going to be at 1. Okay, so there's my horizontal asymptote. All right, now I got to figure out kind of where the curve goes. So let's start by the intercepts. I plug in 0 for x. When I plug in 0 for x, I get 0 over 0. I get 0 over 1, which is legit. That's a legal number. So I get 0. So I do have an intercept 0, 0. If I plug in 0 for y, I'm going to get the same result. So I do have a place where it crosses the x and y axis right there. Now I'm going to plot a couple more points. I just throw in some values. Let's try negative 2. Negative 2 over negative 2 plus 1. Negative 2 over negative 1 is 2. And then I plug in negative 4, I get negative 4/3. I plug in 3, I get 3/4, etc. Once I've plotted a couple of points, I get a general sense of where the curve is going to go. I know it's going to approach the asymptote but never touch it, and so I can sketch my curve accordingly. And there is the lovely version of the same graph with the asymptotes included. Okay, here's another example. Rational functions can have more than one vertical asymptote leading to more than two branches of the graph. Okay, so 1 over x squared minus 4, we can factor that. We get 1 over x minus 2 times 1 over x plus 2. So we know we're going to have two vertical asymptotes, one at 2 and one at negative 2. From a horizontal asymptote perspective, you know, the denominator has a higher degree than the numerator, so we know it has a horizontal asymptote at the axis, x equals 0. And then the question is just where do you put the rest of the curve? Now I've already graphed it with my graphing calculator, but if you only knew where the asymptotes are, but then where to graph points, then just start plugging in points. And these functions are a little more complicated, so they're tricky. You got to be careful. But if I just start plugging in values, I can plug in 3 for x. I get 1 over 9 minus 4, or 1 over 5, and I can plot that point. And then I get 1. When I plug in 1, I get negative 1/3. I plug in 0, I get negative 1/4, etc. So I've just kind of plotted a couple of points. And when I've done a few of these, I get a sense of how these curves are going to lay out. So once I get a couple of points, I can sketch the rest of the graph. Again, it's just grunt work. Once you get your asymptotes, finding the actual curves, you're just plotting points and seeing kind of where they go, and then you draw your curves so that they approach the asymptotes. All right, this one, take a look. X over x squared plus 2x minus 3. Let's go ahead and factor the denominator and see if we can find some vertical asymptotes. I'm going to get them at 1 and negative 3. So I plot one asymptote at 1 and one at negative 3. Horizontal asymptote looks like we have a higher order in the denominator, so I'm going to have an asymptote on the x-axis. So I can go ahead and, oops, I didn't include that, so let's make sure I put that in there. Let's get that horizontal asymptote right, oops, missed, right there. Okay, there's my, it's jumping around for me. Okay, there's my horizontal asymptote. From there, I just want to start plotting points. I could find an intercept here. It turns out that there is an intercept at 0, 0. And then I can just start plugging in points. I could plug in negative 1. Basically, you want to plug in a point from each region. So try a point from out here somewhere, out here somewhere, try a point from out here somewhere, try a couple points in here to see does it cross the axis, does it go up and come down, you don't really know, and then try a point over here somewhere and get a general sense of where these curves are going, knowing that they're approaching the asymptotes. So just pick points accordingly. So I chose negative 1, I got 1/4, negative 2, I got negative 2/3, etc. When I plot those points, I can get a general sense of the curve. Okay, now, sometimes you get what we call, instead of having an asymptote, we just get a hole. So that typically happens when you factor a function and then things cancel out. So for example, we have this function. We can write it as x minus 2 over times x plus 2 over x minus 2. So we know that we have a discontinuity at x minus 2. You can't have the value of 2 and have it work. So there's not going to be there is no domain value at x equals 2. Now, if you were to take this function, though, and continue to simplify it, you would cancel out the x minus 2's and you'd get x plus 2. And that's just a simple linear function. Y equals x plus 2. You have the slope is 1, the y-intercept is 2, and you can just graph that. But when you graph that line, you have to remember that little discontinuity. And the way you identify it is you put a little open circle where the discontinuity is. That's called a hole. So you have to include the hole when you're doing the graph. So let's take a look at the next one. X squared plus 5x plus 4 over x plus 1. If I factor, just ignore the graph on the right for a second. If I graph, or I'm sorry, if I factor it, I'll get x, we'll multiply 4 and add to 5 is 4 and 1 over x plus 1. I know I'm going to have a discontinuity at x equals negative 1. Okay, but those cancel. I'm going to get g of x equals x plus 4. I can graph that. That's just a linear graph. Y equals x plus 4. Y-intercept is 4. Slope is 1. But I have to have that discontinuity at x equals -1, because this denominator, if I find the 0, set that equal to 0, x equals -1. At x equals -1, that's where I have to have my discontinuity. So when I graph my function, my simplified function, I have to remember to include that little hole there. And that concludes our lesson for today.